Hello everyone, I'm Modassar Chaudry from Cardiff University, and I'd just like to mention Lahiru, who's sitting right at the back, who's worked quite diligently on this piece of work, and you can see him at the workstation this afternoon. So the energy supply model interacts with all the ITRC sector models, none more so than the energy demand and transport models. Within energy demand, we look at inputs such as population, GVA, insulation within homes, and use that in a simulation approach to produce spatio-temporal heat and non-heat demands that can be used within the energy supply model. Likewise, within the transport model, we use EV trips, which are translated into a demand for electricity, and the battery size and the capacity of batteries that can be used, again, in the energy supply model, alongside the various elements such as fuel prices, carbon prices, that feed into the energy supply model to allow the model to balance supply and demand. And then we get a bunch of metrics such as energy supply mix, emissions, costs. Additionally, we have a module which we call the energy infrastructure or interventions module, where it allows the user to actually put in interventions, so infrastructure interventions, to allow you to look at various pathways to decarbonize the energy system. So in terms of the model, we have various networks models. On the transmission side of things, in the context of the UK, we have the gas system and the electricity system. On the gas side of things, we have everything from the resources all the way to the terminals, the pipes, the compressor stations, all the way down to distribution systems. On the electricity side, we have all the generation technologies modeled, so nuclear, wind, and gas-fired generators, which are connected to both networks, so it allows that interaction between these two networks at that level, all the way down to energy distribution systems. Energy distribution systems in themselves are modeled via energy hubs. Now, energy hubs allow you to model the energy vectors within a particular local area. So, heat, electricity, gas, hydrogen systems, and the connecting elements between these vectors. So we go all the way from resources, transmission, all the way to end use. So overall, it's an integrated model that we have. So it looks across all the vectors across multiple spatial scales. It's built upon an optimization framework, so we're minimizing costs of the whole system. We can look at local energy systems using our energy hub concept. So it allows you to look at or investigate alternative supply systems locally. It allows you to simulate energy demand for transport as well. We have various other functionalities within the model as well. We have bidirectional electricity interconnector flows. We have demand-side management, so load shifting from peak periods to off-peak periods. We have a module which looks at realistic weather patterns and how that impacts wind generation in particular, and PV as well. And of course, the whole essence of the ITRC project is these interconnections with all the other sector models. So in terms of what the actual networks look like, on your left-hand side, you can see the GB gas and electricity transmission network. So we have that modeled within the ARC analysis, which I'll talk about in a moment. And then we have the connections from these transmission points to energy hub regions, which we have regional energy hubs, so 29 hubs in there. One thing to point out, the model is totally flexible. So if you require something far more detailed than this, the model can handle that. So in terms of the ARC analysis, 3 of these energy hubs are within the ARC region. And we applied the scenarios to this, and we had very specific heat supply system strategies, which I'll talk about in a moment. So we had these 3 strategies, which were mainly around full electric. So you electrify the whole heating system. So you have heat pumps, resistive heating, and electric boilers. You have something that we call green gas, and this is injection of hydrogen into the gas system, or repurposing the gas system for hydrogen-only use. And then we had one called district heating networks, where you had the majority of district heating systems around the arc, but within the green gas and district heating system, we also had obviously electrical systems and gas systems in there. So they are truly multi-vector solutions in there. So in terms of the results, this is what we got. Annually, we saw energy demand fall in electric strategies across the scenarios from 2015 to 2050. And this is mainly due to efficiency gains, insulation of homes, and some of the high efficiencies of heat pumps. So we saw a reduction in energy demand annually in 2050 for the electric scenarios. In terms of the electricity supplies, or electricity demand, I should say, electrification of heating obviously increases or doubles the annual and peak electricity demand from 2015 to 2050. Lower levels in the other strategies. With gas demand, we saw a wholesale reduction from the green gas and from the heat network strategy dropping to around 50% from 2015 values, 2050, and a massive decrease in the electrification scenarios, up to 90% reduction in gas demand. In terms of energy supplies, the top row shows the heat supply and demand, shows the 2015 and selected strategies for the scenarios, which we've shown electric and heat networks there. And as you can see, we have a drop in heat demand compared with 2015 and 2050, around 20-25% reduction, and again, mainly driven by insulation and efficiency gains. The electric scenario, as you can see, is mainly driven by heat pumps, resistive heating and electric boilers. Within the heat network strategy, mostly from various CHP technologies and a bit of heat pumps in there as well. On the electricity side of things, upwards of around 25% of the electricity demand is met by EVs across the scenario piece. So quite a high percentage. The other parts are met by renewables within the ARC region, and within the heat network strategy, some CHP. But in all cases, we still saw substantial supplies from the transmission network, more so in the electric strategy than the heat network strategy. So in terms of emissions, the emissions in the ARC region are roughly around 12 million tons per CO2. Across all scenarios and across all strategies, that drops. In the electric strategy, it drops quite a bit. In the other strategies, less so. In the electrification, mainly, it's essentially the reduction takes the residential and commercial emissions to near zero in 2050. So the part that you see there at the moment is mainly on the industrial side of things, which is quite difficult to decarbonize. Okay, so this complicated looking diagram essentially shows the annualized cumulative costs of implementing each energy strategy for the scenarios. So it's a per household figure per annum. So you see the bar charts there, essentially shows the cost breakdown for the baseline scenario. So you see the cost divided into network costs, operational costs, and capacity costs. And you see the dotted line going across, that shows the 2015 numbers. And you see the dashes on each bar chart, that shows the scenarios, the difference between the scenarios. And what you see straight away is that the new settlements and expansion scenarios have the lowest cost per dwelling per annum. And that is mainly, again, due to insulation within, or easy to implement insulation within new builds and economies of scale that come into play. Electrification has the lowest strategy cost overall across all the strategies. So it's roughly £100, 100 odd pounds higher than 2015 by 2050. The green gas has the largest operational cost, and that's mainly due to the production of hydrogen, which is still expensive in 2050. With the heat network strategy, it's the highest cost that we see across all the scenarios, and that's mainly due to the capital costs of laying down pipes and some of the assumptions that we made around CHP, which we don't really see costs dropping out to 2050. So overall, with all the analysis, we would say the electrification of heating does seem like the most promising way or the most cost-effective way to meet emission targets across the Arc region. Thank you very much.